Hi there, I'm Robin Lineker, and today we're going to be talking about best practices and performance tuning for Splink. So a quick outline of the talk today. First, what is Splink? Second, I'll talk a little bit about how it works. I'm going to introduce a framework for helping us think about best practice and to help with the intuition. And second, I'm going to talk about specific best practices in the context of that framework. So what is it? Well, Splink is an open source piece of data linking software that we've written that uses PySpark. It estimates Falegy-Sunter parameters using the expectation maximization algorithm, and it works on big data sets of 100 million records plus. It works pretty fast with runtimes generally below an hour. And one of the things that's quite important about the code base is that it's got a full suite of automated unit tests, which means that we can be confident about its robustness and correctness. So this talk is about how to get the best possible results out of Splink. Before moving on to specific best practice, I want to talk a bit about what Splink does, and this is going to allow me to introduce some concepts and intuition that provide a kind of framework for thinking about what Splink is doing. These concepts can then help explain and tie together the various best practices that I'll talk about later. So at the core of Splink is the expectation maximization algorithm that Splink uses to estimate model parameters. So this is an unsupervised machine learning algorithm. Specifically, it's an algorithm that learns optimal data matching weights from the dataset of record comparisons. For instance, when deciding whether a record is a match, how much weight do we give to gender relative to, say, a match on first name? This gives us a framework for thinking about how best to use Splink, and it means that we can dip into the standard set of tools and ways of thinking that we use for any machine learning problem. So in that kind of machine learning tool set, two things in particular stand out. The first is feature engineering. How can we transform our data to help Splink learn as much as possible? And second, how can we avoid confusing Splink with, let's say, bad data or bad configuration? That could be overfitting or the algorithm converging to a local rather than a global maxima. Much of what I'm going to talk about today can be thought of in those terms. A second ingredient that we're going to use to help structure our thoughts is a better understanding of exactly what Splink is trying to learn. In a nutshell, Splink is looking to exploit differences between subsets of record comparisons, and it's looking specifically at differences in the likelihood that members of different groups represent matches. So, for example, it's likely that record comparisons where first name matches are more likely to be matches than record comparisons where the first name does not match. The greater the difference, the more precise the matching will be. So we try to do feature engineering to find clever ways of defining subsets of data that maximize the differences. One thing that's important is the way Splink combines information on different groups. It uses the assumption of conditional independence, which means that it just multiplies the probabilities together. For instance, if we observe a match on the first name field and on the surname field, well, all Splink does is it kind of looks at the matchiness of first names and the matchiness of surnames and then multiplies those probabilities together. This can often be unrealistic, and that means that it can result in double counting. So a large part of optimizing a Splink job is configuring the job to mitigate the impact of the failure of this assumption. For example, we'll see later on that if we include two different columns that are both really just measures of a person's location, that can cause problems. So the rest of this talk is now going to delve into the various customization options that you can use in Splink to help optimize your jobs. And to make things tangible, we're going to focus on the settings for this simple data set here. There's only two rows there, but we imagine there's many more. That final column is office location. So the first task is to generate a dataset of pairwise record comparisons from the input dataset. And the main purpose of Splink is then to estimate a match probability for each record comparison. With datasets of any significant size, we can't just compare every record with every other, because we end up with literally trillions of comparisons. Most of these comparisons, such as Robin Lineker versus John Smith, are implausible, so Splink offers an approach called blocking to eliminate implausible matches and reduce the record set of comparisons to something that's computationally tractable. So in the settings dictionary above, which is shown at the bottom of the slide, we're going to be blocking on date of birth, which means that we're eliminating all comparisons where date of birth doesn't match. This would be great if date of birth had perfect data quality. The blocking rule would eliminate only true negatives. But in the real world, this comes with a risk that we might miss potential duplicates in this dataset. That could be due to missingness in the date of birth field, or it could be due to typos or other typographical errors in the data. And this leads us to a bit of a problem. Empirically, it's usually almost impossible to find a single blocking rule which reduces the number of comparisons to a manageable level, but at the same time doesn't make any mistakes, which is to say it doesn't remove any true matches. Splink therefore allows the user to specify multiple blocking rules. So if we look at this settings object, we've now got multiple blocking rules. This is going to generate record comparisons where date of birth matches, and record comparisons where office location and initials match. And what Splink's going to do is it's going to generate those comparisons, make sure that they're deduplicated so we don't get the same comparison twice. So add all of those comparisons to our list of record comparisons. A word of caution here though, a lot of care must be taken when using multiple blocking rules because certain combinations can essentially break the underlying statistical model. The explanation for this is quite nuanced, so we're not going to have time here to discuss it. For now, we'll just carry on building our settings dictionary. The next decision after we've decided on the blocking rules is to pick which columns we want Splink to look at when computing match probability. Generally, this is fairly straightforward. What we do is we just put in every comparison column that contains useful information about whether it's a match. The main trap here is putting in multiple columns that contain essentially the same information. So in this example, we don't include initials because that can be derived from name, and including it would double count this information. This is due to the conditional independence assumption I mentioned earlier. If you look at the settings dictionary at the bottom there, I've also omitted the office column because it may contain information that's too similar to postcode because they're both measures of location. The next thing we need to do is configure the number of levels for each comparison column. What does that mean? Well, consider the first name column, and let's say we set num levels to 3. Remember that we're seeking to exploit differences in the distribution of matches between different subsets of the data. So for a first name field, it's reasonable to assume that there may be a different match rate amongst 3 different groups in the data. First, the group of record comparisons, where first name matches exactly. Second, the group of record comparisons where first names are similar, but they don't exactly match. So that might be Rob versus Robin, for example. And then last, the group of record comparisons where the first names are not even similar. So John versus Robin, for instance. And we would expect there to be different proportions of matches in each of those 3 groups. So when we set the number of levels to 3, Splink creates 3 groups, and what that does is ensures that Splink is going to estimate separate parameter estimates for each of the 3 levels. Splink will then output charts that tell us how the estimated match probability is influenced by the different levels. So if we look at the top chart on this slide, what it's telling us is that level 0, which corresponds to no match, has a negative effect on match probability. Level 1, a partial match, increases the probability of a match, but only a little bit. And level 2, which is an exact match, pulls up the match probability a lot. What would have happened if we'd only used 2 levels, let's say exact match or not exact match? In this case, the not exact match group contains both names that almost match, like Rob and Robin, and also ones where they don't match at all, like Robin and John. And what the algorithm kind of has to do is to take an average, which means that the final match scores, we lose precision in the final match scores. So what we'll see is that the almost matches will be scored down too harshly, and the does not match at all comparisons won't be scored down enough. By choosing the 2 levels rather than 3, we've essentially destroyed information. And we can see this in the second chart at the bottom of this slide, where the level 0 record comparisons are pulled down a bit, but not much. It's important to mention the trade-offs here. Taken to its logical extreme, we could consider having a very large number of levels to account for all the subtle differences in distributions between groups of records with slightly different characteristics. So, for instance, we could have one group for each value of the edit distance. There are 2 downsides to increasing the number of levels. The first is overfitting. Essentially, the more levels you have, the more parameters you have. And the more parameters you have, the more likely estimates are to be influenced by specific characteristics of your training data, rather than be representative of the overall population. And the second downside is computational complexity. More levels, essentially, just means more compute time. So we understand now what's meant by the levels, but we haven't talked about how these levels are computed, precisely how a record comparisons assigned to the different levels. We also want to think about why we're doing this. Well, consider the example of first name again. Remember that we're trying to create 3 different groups of record comparisons that have distinctly different distributions. In the middle group, we want names that are similar but don't match exactly. So we want to define don't match exactly in a way which really drives a wedge between implausible matches, let's say Teddy versus Freddie, and plausible matches, things like Rob versus Robin. A simple edit distance function like Levenstein won't make this distinction very well. We'll probably want something like Jarrow-Winkler or D-Metaphone, which are designed for this purpose of comparing names. So how do we do that? Well, in the settings object, we can provide a custom SQL expression that is shown at the top of this slide. And we recommend providing custom case expressions that attempt to maximize the difference between groups. This functionality also provides the answer to a common question about Splink. How can I deal with a numeric field? Well, you just need to write a custom SQL expression that does something like looks at the absolute difference in the numerical values and assigns the comparison to different levels based on the absolute difference. In terms of comparison functions available in Splink by default, we provide a jar with native Scala implementations of the following functions: Jarrow-Winkler similarity, Jacquard similarity, cosine distance, and D-Metaphone. So now we've chosen our comparison columns, we've chosen the number of levels, and we've written some custom case expressions. A common problem in data matching that we might still have is we might have unbalanced term frequencies. So for instance, we might have more Johns than Robins in our dataset. We're not talking here about the cardinality of the name field, which is the number of different names in it. Splink's going to automatically take account of cardinality for every single field by default. That's why estimated match rates on really distinct fields like social security number, they'll be greater than on a field like, let's say, gender or name. With term frequency adjustments, we're specifically talking about unbalanced distributions, like there being more Johns than Robins. If we don't make term frequency adjustments, Splink will take an average of everything, so it might give excessive weight to a match on John and not enough weight to a match on an unusual name like Robin. It's therefore good practice to set term frequency adjustments on fields where there's a substantial skew in term frequencies. It's worth noting that this is essentially equivalent to having a different level for each unique name in the dataset. However, the computational complexity of trying to estimate during the expectation maximization step is too great, so they're made as an ex post adjustment after the main weights have been estimated. What we've seen so far provides a good foundation for our settings object, which may be enough for many applications. The next couple of slides are a bit more advanced, but they also show why Splink is very adaptable to many different data linking problems. So I previously advised not to include two columns that are highly correlated in the sense that they essentially measure the same thing. I'm calling this sort of multi-collinearity, but in inverted commas, because it's not exactly accurate to call it that. So in our data example, postcode and office are a possible example of this. So you may even be able to predict office with almost 100% accuracy if you know postcode. In what we've done so far, that's led us to drop the office field from our comparisons. But it's quite common that lower granularity fields like office have lower missingness in the data than the higher granularity fields like postcode. So how can we use the higher granularity field where it exists, but sort of default back to using the lower granularity one where postcode doesn't exist? What we can do is we can define a custom field in our settings dictionary and a custom case expression for it. So the pseudocode here is if postcode exists and it matches, we'll assign it to level 2, which is the highest level of matchiness. If postcode is null, but office is not null, and it matches, assign it to level 1. So if postcode is null, we look at the office location. If that matches, assign it to level 1. And otherwise, set this comparison to level 0. We can actually go be a little bit more specific. We can be a little more sophisticated than this in real jobs, and we can do things like look at the latitude, longitude, and say assign the highest level of match to lat longs within 5 kilometers of each other, a second level for 20 kilometers, and then maybe fall back on the less well specified geographic fields like office, where we don't have the postcode. The important point here is that it's better to put all location information into a single comparison column than put it in multiple different comparison columns and risk double counting. We can also use this custom functionality to deal with a bunch of other different features of our data. So we can use it for things like name inversions, where sometimes we might have John Smith in our data set, and sometimes the surname and forename might be the wrong way round, so we get Smith John. In that case, we would write a custom case expression that says, if surnames match, make it level 2, which is the highest level of matchiness. If surname matches any other name field, so if surname matches first name, assign that to level 1. And then if there's no match of surname against any name field, assign it to level 0, the least level of match. Another issue that comes up in data matching is that information changes over time. So how should we weight a mismatch on address if the two data points were collected 10 years apart? People are quite likely to move in that time. It might be quite different for if we're comparing two records which were both collected recently. Again, we can assign different address comparisons to different levels based on their sort of vintage of the data. And finally, we can even make these record comparisons asymmetrical. So we have one example, for instance, where we're seeing cases moving between different stages of casework, and they're moving between different administrative systems. And we know they always move from system 1 to system 2, and we're trying to match the cases. So in this case, we expect records in system 2 to have a timestamp which must be after the timestamp of the records in system 1. And again, we can write a custom expression that assigns to level 2 the highest level of matchness only in the case that the timestamp in the second system is after the timestamp in the first system. So that just gives a bit of a flavour of the kind of amount of flexibility that this functionality can give us. So moving on to the conclusions of the talk. First of all, optimizing matching using Splink is as much an art as a science, really. And the best way to go about it is to develop a solid understanding of how Splink works and the kind of pitfalls you can fall into. What we typically see is that carefully considered and heavily customized settings will typically give you the best results, and you often need to just try a lot of different things. And finally, I just want to say that a more complete explanation of everything I've talked about in this presentation, plus a discussion of diagnostic charts, so looking at some of the charts that come out of Splink to find problems, Also a discussion of starting values for your iterations, and a bunch of other stuff is available at the URL shown on that slide. Thank you very much for listening.